Hello everybody. Sorry I'm not there today, but I am out sick. Fortunately, I've prepared a wonderful physics presentation for you. Won't be too long. We're going to go over the definition of refraction and how it's different from reflection, which is what we did last time. And once I finish this, which I hope shouldn't take too long, you can then spend some time working on a lab using the laptops on the side. It is an Explore Learning Lab, and you will need the handout by the door if you haven't got it yet. We are going to have a concept check over this material, but it's not going to be today, so I will show you the preview. After we got the preview, we'll go on from that point. And here we go. The diagram below represents the propagation of a light wave passing from medium A into medium B. As the waves enter medium B, the speed of the waves what? Now, if we look at our choices here, they're pretty basic, but the language in the question is slightly advanced. So let's go over some of the words. Propagation. In physics terms, propagation of a wave means the traveling of the wave, how the wave moves. So when it says the propagation of a light wave, what it means is the travel or the movement of a light wave. Also, we've got medium A and medium B. Medium is a word we've gone over in class before. It means halfway in between small and large, right? Wrong. Medium means material, as I'm sure a lot of you guys remembered. So medium A and medium B are two different kinds of stuff that the light is traveling through. So you could rephrase this sentence as, the diagram below represents the movement of a light wave passing from material A into material B. As the waves enter material B, the speed of the waves blank. And we're going to talk about that. Number 2, if red light travels at a velocity of 1.5 times 10 to the 8th meters per second through a material, what is the index of refraction of the material? So there's a bit of math in this. Hooray, math! Take a look at this number. This is a speed, but it's also not the speed of light that we've mentioned before in class. That's because the speed of light that we've mentioned in class, that 3 times 10 to the 8th power, is the speed of light through a vacuum where there's nothing in the way. Today we're going to learn about how light moves when there is stuff in the way, which can change our speed. Number 3, a ray of light travels from air to water at an angle of 40 degrees from the normal in air. What is the angle of refraction in water? So first off, we are going to have to learn what is angle of refraction in the first place. What does that even mean? It's not the same as angle of reflection, which is what we learned about last time, but it's a little bit similar. Also, we've got some values up here, n of 1 and n of 1.33. We're talking about normal lines and things like that. So there will be some WTF math in this unit. And finally, number 4. Through which of the following does light travel the fastest? And I'm willing to bet that some of you could answer this right now based on your memory of previous units. If not, that's okay, but you might remember this. So here's the notes. Here we go. You should have your packet out. We're on the top of the right-hand side of the page, I believe. But anyway, the question we're answering is, what is refraction? Refraction. Refraction is the bending of a wave as it passes at an angle from one medium to another. There's a lot to unpack in that sentence. We've got the bending of a wave. It's passing at an angle and from one medium to another. So in other words, what we have here is a situation where if we have a barrier between two mediums, and perhaps we've got air on one side, there's air over here, and there's glass over here, as the light wave travels towards that medium, and it has to be at an angle, remember, as it travels towards that medium, and then it passes from one medium to another, what we get is a bending of the light. It changes directions. Now that was a little bit sloppy. Let me see if I can fix that. There we go. Here we go. A bending. So there's a clear difference in those directions right there. Light changes direction when it goes to a new medium. Now we'll talk about why this is, but make a note. If the wave passes into a new medium perpendicular to the surface of the new medium. Perpendicular, in case you've forgotten, is that right angles, right? Just like the normal line. If the light goes in perpendicularly, the light will not bend. It'll just pass straight through. And like I said, we'll say why in just a moment. The takeaway is, for refraction to happen, two things must occur. The wave's got to hit the new medium at an angle, and the medium has to be transparent. The new material has to be a material that light can travel through. If I'm going from air to glass, or from glass to water, or from air to jello, all of those are things that light has no trouble traveling through. However, if I'm going from air to steel, it is a new medium, but it's not transparent, and so we're not going to get any refraction in that case. Here is a picture of a light ray, right here, going from medium 1 into medium 2, traveling. And as that light ray hits, bing, it changes directions right there. I have an animation I'll show you when I get back, but I have a metaphor that might work. If you were roller skating down the road, and as you roller skate, you brake with one of your feet. So you hit the brakes with one foot, but not the other one. As you roller skate, let's say you stop with this foot right here and not the other one. Look down at your legs, let's call it your right foot. So you're moving and you brake with just your right foot. What's going to happen to your direction? You're going to turn because your right foot is slowing down, but your left foot can just keep going at its old speed. So you turn towards that slower foot. If you've ever worn Heelys before, you've seen this phenomenon, or ridden an old-fashioned go-kart, or dragged your feet when you're riding on the shopping cart at the supermarket, or ridden in a canoe or a rowboat. If one side slows down, you turn towards that side. That's the same thing that happens with the light. As the light moves down towards the material, let's say that this light beam now, we're going to widen it out, we're going to magnify it like this. As that light hits that new material, part of the light, this part over here, is going to hit that new material before the other part of the light. And when it does, this side slows down faster than this side, giving us a change in direction in the material. Now, if that seems weird, I know we don't have an animation here yet. If that seems weird in your lab today, you're going to see some animations of it that should make it make a little more sense. But as a summary, when a light ray is passed from a low density material, into a high density material, its ray is bent towards the normal. Remember, the normal is that imaginary 90-degree line we've got perpendicular. And just like with reflection, we have theta I, there's our angle of incidence, and theta R, but here theta R is angle of refraction, not angle of reflection. When an angle is reflected, the initial angle and the final angle, which would be over here, I guess, if it was going off of that material, would be the same. That is never true of refraction. The whole point of refraction is that this initial angle, the incident angle, does not equal the refracted angle. Here is an acronym to help you remember this. FAST. As light travels, if it goes into a faster material, it bends away from the normal. So what I mean by faster material, here's our boundary between two materials, and we have maybe air, and I like my Jello example. We got Jello right there. Which one of these is more dense? Now, hopefully all of you knew that Jello is the more dense material. Air is a less dense material. And as we saw earlier in this slideshow, the denser a material is, the slower the light travels through that material. Light is fastest in a vacuum where there's nothing. But the more stuff that the light has to pass by, the slower the light's going to go. Now here's our imaginary normal line. As a beam of light goes from air into jello, I guess I'm going into slower right now. As a beam of light goes from air into jello, it's going into a slower material, a more dense material. So it bends towards the normal. This is more like the normal line as we go in that way. If it's leaving the jello and going into the air, that's a scenario where the new medium, because going from jello into air, would be faster, and so we bend away from normal. So it would look more like this. It would, let's see here. If we go from jello into air, we would go upwards and then bend away from normal. So FAST. If you're ever unsure, just remember the FAST acronym. This is why if you're ever spearfishing or bow fishing, or if you just want to play like you're Tom Hanks in Castaway and try to catch a fish with your bare hands, it's more difficult than it looks because the fish is not where it looks like it is. And that's due to that refraction of the light. The light that's hitting your eye is bouncing when it goes from water into air or from air back into water for the fish's eyes. And so where you see something is not where it really is. That's why when you put a straw into a glass of water and look at it from an angle, the straw looks to be bent or broken because of that refraction. Here are some values for what we call index of refraction. Index of refraction is a measurement of how much the light gets bent. Now in a vacuum, the index of refraction is 1. There's no bending. And in air, it's 1.0001. There's minimal bending there. But in water, it's 1.33. You get a significant change in direction. In ice, it's about the same. Glass is more so. Diamond, I just had a recording error. In case you couldn't hear my last sentence, diamond is even more so, or bends light even more so, because diamond has a higher index of refraction. So a high index of refraction means that it's a denser material. It'll bend light towards the normal. A low index of refraction means that it is a less dense or more diffuse material. And here's our math. So exciting. Our math that reflects this. N, or the index of refraction, is equal to c divided by v, where c is the speed of light. In a vacuum, that's that 3 times 10 to the 8th that Einstein told us about. And v, which is the velocity in the new medium. So n is just a ratio of the speed of light, which I kind of misspoke. Einstein didn't discover it. We just remember it because we know E equals mc squared. I mentioned it the other day. And the velocity of light in this new medium, no longer in a vacuum. So we're always going to know c, that's 3 times 10 to the 8th. The other two will be our unknowns. The bigger this value, the bigger the index of refraction, the more the light is going to bend. And there are no units for this, it's just a number. So let's calculate the index of refraction for a material if light travels at 1.5 times 10 to the 8th meters per second through it. This is a WTF style problem. So let's take a look at what's being offered. First question is, what does the problem want? Okay, it wants index of refraction. So n equals question mark. That's what we don't know. And it says light travels through it at, so it tells us a speed. That's a velocity right there. 1.5 times 10 to the 8th meters per second. We don't have quite enough information unless you remember that we always know c. c is a constant value, 3 times 10 to the 8th meters per second. So there's our want, what it wants, and here's what it tells us right here. The only equation we know for this, our formula, is N equals C over V. So in this case, N is 3 times 10 to the 8th divided by 1.5 times 10 to the 8th. Sorry, it's getting a little cramped in here. N equals 2. Our index of refraction for this material would be 2. Here's our other big mathy equation right here, Snell's law. It looks like pre-cal, it does have some trig functions in it, but I guarantee you we're going to do it in a very, very easy manner. The index of refraction for a material can be used to figure out how much a ray of light will be refracted as it goes from one medium to another. Or in other words, if you don't know the velocities, you can still find n by comparing the angle of incidence to the angle of refraction. We've got the sine key here, or the sine function, but remember your calculator has a sine key, which is going to make this pretty trivial to do. So here's an example of us rearranging some of the math in this case. Here is Snell's law. Now let's plug in some numbers. Maybe here's our index of refraction for the first material. There's our angle of incidence. Here's our index of our angle of refraction. And we don't know n. We don't know index of refraction for the second material. Now that equation right there looks a little hairy if you're easily intimidated by those sine functions there. But like I always say, if the algebra is not your best friend, if you're feeling uncomfortable, remember, all of this is just a number. You have a calculator that's going to do the hard part for you. So instead of rearranging now, while it's all separated, make it into numbers, combine what you can, and then do the algebra. So press sine 30 on your calculator. You should get 0.5. If you don't get 0.5, it's because your calculator is set to radians. The key at the top, second from the top left, right next to the second key says DRG. That'll help you change it back into degrees instead of radians. Sine of 30 is 0.5. So now we have 133 times 0.5. That's an easier number to do. Sine of 30.53 is 0.508. So now we have an equation that is not nearly as intimidating to work with. We've done this before. Those two numbers combined give me 0.665. And then to get rid of this 0.508, I divide both sides by 0.508. 0.665 divided by 0.508 gives me an index of refraction of 1.309. So as long as I don't let these sine functions scare me too much, the math here is pretty straightforward. But what if, I hear you asking, what if we're trying to find this? Well, you're in luck. Here's another one where we're trying to find theta. So same equation, Snell's law. Same values. We've got the sine of 30, and now we've got 1.309 for our index of refraction for the second material, and the angle of refraction is the unknown. First, simplify everything the same way we just did. Sine of 30 is 0.5. 133 times 0.5 is 0.665. Get rid of that 1.309 by dividing, and you end up with the fact that, hold on, let me get the right pen right here, 0.508 is equal to sine theta r, or the sine of the angle of refraction. Now, we have got to do something about that sine. And I did not realize that this slide has this. You do not divide by sine. No, forbidden, cardinal sin, don't do it. Because sine is not a number, sine is a function. So if we're trying to get rid of this sine right here and get just the theta instead, we're going to invert the sine -1. Now, if you're in pre-cal, if we want to use trig, we'd be using secant for that. But fortunately, you don't have to. You don't have to know anything at all, because second sine is sine -1. So if you want to find this number, To get rid of sine, you take second sine of 0.508, which should give you 30.53 degrees, which we know from our previous slide is what we're trying to get here. This changing of the angle of the light ray as it goes from one material to another is why you get things like Pink Floyd's Dark Side of the Moon album cover, or anything else with prisms, why light shines through a raindrop or a crystal and gives you a rainbow on the other side. Because the amount that the light bends or refracts doesn't just depend on the medium, it also depends on the wavelength of the light. So if you look at a beam of white light entering a prism, it separates into the colors of the rainbow on the other side. Blue light, that low wavelength light, refracts more. Lower the wavelength, the more the refraction. So the blue component of the white light, remember white's made of all the colors, bends the most as it exits the material. Red bends less, and all the colors in between bend in between amounts, meaning instead of a single beam of white light, we are left with a rainbow of all the colors on the other side. Now this is our last slide for today. We're not going to do the concept check today. You'll do that when I get back. If you have any questions, I'm sure that the substitute would be more than willing to rewind this video, show you some of the previous slides if you need to see them. Once everyone's got the stuff, it is now time to do your lab. It is an Explore Learning Lab, www.explorelearning.com. You all have logins. I want you to work in groups of 2 or 3. We only have about 14 computers for this class, so there's not enough for everybody to have their own, unless it's his first period, and I think that's going to change too. But anyway, work in groups. Go to explorelearning.com. If you've forgotten your login information, the substitute has the class key so you can open a new account and do the lab. If you finish it today in class, I would love for you to turn it into the box. If not, it is due when I see you next time, which would be Tuesday. And I know some of you guys are going to forget about it, so try your best to finish it in class today so that you don't end up forgetting and not having it ready on Tuesday. I hope that you guys have a great day, and I'll see you all when I get back.